Hey there, AP Environmental Science class. Welcome back to part 2 of my lecture on chapter 16, where we're talking about environmental hazards and human health. We spoke about in the first part of the lecture about infectious diseases and how that affects human health. Now we're going to move on to chemical hazards and talk about how those hazards can affect human health. So, how do chemical hazards threaten human health? Well, certain chemicals in the environment can cause cancers and birth defects. In addition, they can disrupt the human immune, nervous, and endocrine systems. All right, and that's what we're going to talk about as we go through the next couple of slides. So, some chemicals can cause cancers, mutations, and birth defects. Toxic chemicals. Here are some terms for you. So, a carcinogen are chemicals, types of radiation, or certain viruses that cause or promote cancer. Mutagens are chemicals or radiation that cause mutations or increase the frequency of mutations, and teratogens are chemicals that cause harm or birth defects to a fetus or embryo. So just understand carcinogen, mutagen, and teratogen, what those three terms mean. So first case study was something called PCBs are everywhere, a legacy from the past. PCBs stand for polychlorinated biphenyls. And they are a class of chlorine-containing compounds. They're very stable, they're non-flammable, but unfortunately, they break down slowly in the environment. They can travel long distances in the air. They are fat-soluble, and they are biologically magnified in food chains and food webs. Now banned, but they are still found everywhere, these PCBs. So again, this was a legacy from the past. And again, this is the biomagnification we speak about with these PCBs. Remember, in water, you can get a very small fraction, but as the phytoplankton that live in the water grow, again, we see a tenfold increase, right? And then the zooplankton, which eats the phytoplankton, again, another tenfold, et cetera, rainbow smelt. Get eaten by lake trout, get eaten by the herring gull, and then by the time we get to the herring gull eggs, 124 parts per million of PCBs, and that obviously destroys the eggs and can give obviously an issue to the reproduction of those herring gulls. So again, this is what we're talking about with biomagnification. We're going to talk about it a bunch over the next couple of slides because again, when it comes with toxic chemicals in the environment, the problem with many of them is they do get biomagnified as they go through the food chain. So by the time it gets to us, right, we're one of the highest parts of that food chain. Okay, by the time we eat some of these organisms, the amount of PCBs, or we'll talk about mercury or any other of these chemicals, get magnified, and so by the time we ingest them, there's a lot more of those chemicals present than, let's say, at the bottom of the food chain. Okay, and again, this is that biomagnification that we've spoken about. Some chemicals can affect our immune and nervous systems. All right, what is our immune system? Our immune system protects the human body against disease. Arsenic, methyl mercury, and dioxins can weaken the immune system. So again, just some types of chemicals that can wreak havoc on the immune system. Neurotoxins can harm the human nervous system. Examples, those PCBs we just talked about, arsenic, lead, and certain pesticides, methyl mercury as well, especially dangerous as a neurotoxin. So you'll notice some of the same type of chemicals are going to pop up frequently throughout the slide. So again, make sure you just have a general understanding of what these chemicals can do to the human body. So once again, just kind of another picture that shows you how these chemicals can get into the environment, into the food chain. And again, also talks about that biomagnification. Again, the phytoplankton to smaller fish, to larger fish, and then eventually to us catching that fish. And again, just a graphic just kind of showing you how some of these chemicals, hazardous chemicals, can get into the food chain. So again, just kind of understand what's going on here. Kind of take a look at this graph and again, just kind of understand the interactions between the pollution and the organisms and how that then magnifies or biomagnifies the chemical content. So by the time we get it, by the time we eat that larger fish, it has much more of those toxic chemicals in them. All right, so some chemicals can also affect the endocrine system. What is the endocrine system? Well, that systems, they're basically glands that release hormones that regulate bodily systems. They control sexual reproduction, growth, development, learning, burning ability and behavior. Hormonally active agents called HAAs, also called endocrine disruptors. They have similar shapes and bind to hormone receptors, and there will be a diagram about this coming up a little bit later on. So, continuing to talk about the endocrine system, again, mercury, a big issue when it comes to affecting the endocrine system. What are some prevention? Phase out waste incineration, remove mercury from coal before it's burned, or switch from coal to natural gas and renewable energy sources, or we can control the amount of mercury in the atmosphere, sharply reduce mercury emissions from coal burning plants and incinerators, label all products containing mercury so you know what you're getting, and collect and recycle batteries and other products that contain mercury. So here's what we're talking about when we talk about these normal hormone processes. These are those HAAs, or those hormonally active agents. Again, on the left side, normal. All right, you have the receptor on the cell. Here is the hormone, and it recepts to the cell. However, some chemicals, estrogen-like chemicals, for instance, are a hormone mimic. So they're not what the actual hormone. They mimic the hormone and then can get basically put on the receptors here. And that can obviously cause some toxic issues, because you have this now chemical that has mimicked what the natural hormone should be, attaching to the cell. And eventually that's going to kill the cell. And then we have hormone blockers, anti-androgen chemicals, for instance, that actually get in here and block any of the other hormones from trying to get in. So again, normal on the left, the two on the right are disruptive. And again, this is what some of those toxic chemicals in the environment can do to the endocrine system by either mimicking or blocking the natural hormones that would attach to a normal living cell. And obviously, when a mimic or a blocker attaches, the normal hormones can't get in there. And so the cell obviously dies off or mutates, and then you get obviously some issues with toxicity there. So what can you do? Exposure to hormone disruptors. Well, eat certified organic produce and meats, so you know that you're not going to have to deal with any of those toxic chemicals. Avoid processed, prepackaged, and canned foods. Use glass and ceramic cookware. Store food and drinks in glass containers. Use only natural cleaning and personal care products. Use natural fabric shower curtains, not vinyl. Avoid artificial air fresheners, fabric softeners, and dryer seats. And use only glass baby bottles and BPA-free sipping cups, pacifiers, and toys. So again, things that you can do to limit your exposure to hormone disruptors. And again, as you know with these charts, definitely understand, or at least put to memory, a few of those bullet points so you can use them on a potential FRQ. So how can we evaluate the risks we get from chemical hazards? Well, there's ways to do it. One way is by using live laboratory animals. I use them to test. We can case report of poisoning, so we can kind of track them and see what's going on. And we can do epidemiological studies, okay, which obviously look at how these chemicals and how these interact, and how the risk factor, is it high risk, is it low risk, etc. Many health scientists call for much greater emphasis on pollution prevention to reduce our exposure to those potentially harmful chemicals. Obviously, you can do all these studies that you want, but if the pollutant isn't there, you're not going to have to worry about it. So at the end of the day, maybe it's really the emphasis should be on reducing our exposure to those harmful chemicals. So many factors determine the toxicity of a chemical. Toxicology is the study of the harmful effects of chemicals. So the dose, right, the amount of chemical you receive, your age, obviously, is going to determine the toxicity. Your personal genetic makeup, right? Some of us may be able to handle toxic chemicals better than other folks. Multiple chemical sensitivity, called an MCS. Solubility, all right, is that chemical soluble in water? Is it soluble in fat? Persistence, all right, how long it hangs around, or does it basically go away very quickly? And again, that biological magnification that we've spoken about. So all these factors determine the toxicity of a chemical. So synergistic interaction is when the effect of two or more agents interacting is greater than the sum of the agents, okay? That's called a synergetic interaction. And response is either going to be your acute effect, immediate or rapid, or a chronic effect, which is permanent or long lasting. Okay, so this will be how the toxicity in the chemicals affect you as a human. Okay, an acute effect is something that happens immediately and rapid. All right. For instance, you put let's say arsenic in your mouth, you're going to die instantly. Okay, that's an immediate or rapid acute response. A chronic effect is going to be permanent or long lasting. So let's say you're a cigarette smoker and you end up getting emphysema because of that. That is a chronic effect to the toxicity in the cigarette smoke that you've been smoking. Okay, so again, acute effect, immediate, rapid, chronic effect. A chronic effect, permanent and long lasting. So, case study in the book, Protecting Children from Toxic Chemicals. They did an analysis of the umbilical cord blood. 180 chemicals found that cause cancers in humans or animals in that blood. So infants and children are more susceptible. Again, we talk about age. The young and the very old are going to be more susceptible to toxic chemicals. Kind of us, kind of you guys as almost 20-year-olds, 30-year-olds, 40-year-olds, that's kind of middle-aged folks. We are going to have a little bit better of an immune system, hopefully, to be able to deal with this. But again, infants and children are more susceptible. They eat, drink, and breathe more air per unit of body weight than adults. Their exposure to toxins in dust and soil when they put objects in their mouths, okay, a lot more than we do. And they have a less well-developed immune system, okay, to kind of fight off any of these toxins. So scientists are going to use live various tests to estimate toxicity. Usually these studies involve mice and rats. Because they have actually systems similar to human systems, mice and rats, and they're small and they can reproduce rapidly, so we can see the effects of the toxic chemicals over time or over generations a lot quicker in mice and rats than we can, let's say, if we study actual human beings. There's something called a dose response curve, or a median lethal dose, LD50. All right, non-threshold dose response model and a threshold dose response model. I'll show you what they look like in just a second. But basically, the dose response curve, or that median lethal dose, is usually 50. So once you get to the point where more than 50% of the test subjects begin to die off, then we know we have some issue. If under 50% don't die off, then maybe there's not that big of a risk. Okay, so that's kind of when people look at this dose response curve. Basically, the median lethal dose 50. All right, below 50, we assume that the risk to the chemical, the toxicity in the chemical, is low. If we get that LD over 50, then we obviously say that the toxicity in that, or the risk factor, is much greater for the toxins in that certain chemical. All right, and again, this non-threshold dose and this threshold dose response model basically is what you look at here. So basically, the dose is on the x-axis, the effect is on the y. Basically, a non-threshold just means the minute you start dosing, giving any organism this chemical, you have some toxicological effects that begin to occur, okay? A threshold means you have to get to a certain dose level before you begin to see any toxic effects. All right, so non-threshold, the minute you put this chemical into an organism, you begin to see effects. Threshold means you have to put in a certain amount before we begin to see those effects. And again, that's your threshold level, okay? So certain chemicals the body can handle. Some of those chemicals in the body, it's at when we get to a certain dose, a certain threshold, that then we begin to see the effects of that chemical in the body. And then there's an unconventional, which basically doesn't go the way it should be. For instance, here, as the dose increases, the effect increases, but then the dose begins to, let me go back to that. The dose begins to, as the effects decrease, though, as the dose continues to increase. All right, so that's unconventional. We usually don't see that a lot when it comes to toxic chemicals. Usually, as the dose increases, your effect will increase as well. But for some, the dose could increase, and maybe you could see a decrease in effect. I can't really think of one of these right now off the top of my head that would be unconventional. But just realize if you see a dose response curve that looks something like this, it is called unconventional. Okay, most are going to be non-threshold or threshold, and again, the difference between these two is a threshold just means you need a certain amount of the chemicals to actually build up in your body before you begin to see the effect. Non-threshold, that effect becomes right, or that effect comes with that initial dose. So more humane methods than using animals are out there. We're trying to find ways to do this, to test the toxicity of certain chemicals without having to use mice or rats. So for instance, replace animals with other models like computer simulations, or maybe just tissue culture, or maybe just individual animal cells. So instead of taking the whole mouse and exposing it to these toxic chemicals, and then obviously the mouse will probably die or have some adverse effects, maybe just take one or two cells out of the mouse and then use those cells to kind of see how the toxic chemical interacts with those cells. Effects of mixture of potentially toxic chemicals, difficult to determine, all right, because if you have a mixture of all these different types of chemicals in, for instance, the atmosphere, all right, how do you know exactly which one is having the most effect compared to another one? And so sometimes it's difficult to determine. So are trace levels of toxic chemicals harmful? Insufficient data, all right, for most chemicals out there. Unfortunately, we need to have more research. We are all exposed to toxic chemicals, to trace amounts all the time. So again, do these trace levels really affect us eventually, or do we stay under that threshold, meaning that the trace amounts are okay in our bodies? And unfortunately, right now, we have insufficient data for most of the chemicals out there, and therefore we need more research. So this is an interesting graphic here. These are just showing you the trace chemicals that we have basically in everyday products in our home. So for instance, I'm not going to try to butcher some of these names, but you'll notice shampoo has some perfluorochemicals in it to add shine. Food, for instance, some food can contain biphenyl A, that's BPA. All right. Frying pan nonstick coating can contain those fluorochemicals once again. All right. You'll notice imported fruit may contain pesticides banned in the U.S. All right. That water bottle can have that BPA. Computer flame retardant coatings of plastic casings and wiring have some chemicals with it, et cetera, et cetera. Okay, you'll notice the mattress, flame retardants in the stuffing of mattress actually has some toxic chemicals in it. Clothing can contain those perfluorochemicals again. So again, these are just all toxic chemicals that are harmful. Again, they're at trace amounts. Okay, but the question is, are those trace amounts, do you get to a point where that dose curve begins to show the effect? We get to a certain threshold, or do these chemicals really have no threshold, meaning our body can handle them? And once again, the jury is out here. We still need to do more research, but just understand that all of us, every day of our lives, are getting at least trace amounts of toxic chemicals, or at least we're interacting with trace amounts of toxic chemicals. So why do we know so little about the harmful effects of chemicals? Well, there are several limitations in estimating toxicity levels and risks. Only 10% of over 85,000 registered synthetic chemicals have been thoroughly screened for toxicity. Think about that. That means 90% haven't been thoroughly screened for toxicity. Okay, so this is something that we need to do. And again, maybe this is a career path for you. Okay, maybe you're going to get into more of the chemistry side of environmental, or at least the chemical side, chemistry of environmental science, and kind of understanding how these toxic chemicals interact with the chemistry in our body. And maybe, again, that's something that you can do to maybe get that number, that 10% up there a little bit higher. 99.5% of chemicals used in the U.S. are not supervised by the government. All right, think about that. Okay, that means only 0.5% of the chemicals used in the U.S. are supervised. 99.5 aren't. Okay, and so this again is another reason why we know so little about the harmful effects, because no one's really supervising these chemicals, and therefore no one's really doing studies on how they affect. So what we need to do. We need to not only prevent pollution, but we need to employ the precautionary principle. So what is the precautionary principle? The precautionary principle states those introducing a new chemical or new technology need to follow new strategies. What are those strategies? Number one, a new product is considered harmful until proven safe. All right, so it's kind of the opposite of our jury system here in the U.S., right? You're innocent until proven guilty. Well, it's kind of the opposite when we talk about chemicals. The chemicals need to be guilty, and then we need to prove them unguilty in a way, okay? And the way I say that is harmful to safe, all right? You're going to assume your new product is harmful until you can prove that it's safe. That's not going on right now. In addition, existing chemicals and technologies that appear to cause significant harm must be removed. Even if we don't know for sure, even if we haven't done the studies yet to conclude, all right? If they appear to cause significant harm, they have to be removed. So this is the precautionary principle. This is what we need to do going forward. Again, we're not doing this, but again, very important, okay? Consider that new product harmful until it is proven safe, not the other way around. Don't consider it safe until thousands of people die. No, all right? Assume it's not safe until you can prove that it's safe. And in 2000, there was an international agreement to ban or phase out the dirty dozen persistent organic pollutants, otherwise known as the POPs, all right, to kind of help with pollution as well. In 2007, the European Union enacted REACH, R-E-A-C-H, which requires registration of untested substances. Most hazardous substances not approved for use if safer alternatives exist. All right, so the European Union basically said they're basically taking more of a control of these substances. They're requiring a registration if it's not tested, and they're basically saying that if you have this hazardous substance, if there's a safer alternative, we're not approving that hazardous substance. Go use the safer alternative. In 2011, the EPA here in the U.S., the Environmental Protection Agency, issued new pollution prevention standards, which in part dealt with mercury emissions from coal burning plants. And there was the Minamata Convention, which its goal was to reduce global mercury emissions. So again, we're trying to do this, all right? We have that precautionary principle that we're trying to use to prevent pollution, and over the past 20 years or so, there have been some laws and some conventions that have tried to reduce the amount of toxic chemicals that are polluting the environment. So, case study: pollution prevention pays. So the 3M company, you guys know 3M, okay? From 1975 to 2015, they prevented more than 2 million tons of pollutants from reaching the environment, which actually saved the company almost $2 billion, okay, over that span. Think about that, guys, all right? This is so important, and this is something you guys need to go out there as the next generation that's going into the workforce, and you need to explain to folks that preventing pollution saves money. It saves money. Initially, maybe it doesn't. Initially, maybe you got to put that regulator on your smokestack, but over time, okay, the pollutant, decreasing that pollutant saves the environment. And this case study proves it. 3M proves it. They prevented 2 million tons of pollutants reaching the environment and saved almost $2 billion. There was also an employee reward program for projects that eliminate or reduce a pollutant. So again, give folks an incentive to figure out ways to use our brains, right? We have the biggest brains on the planet. Let's figure out how to eliminate or reduce pollution. And again, giving people an incentive like an employee reward program. It works. 3M proves it. Okay, so it works. So how do we perceive and avoid risks? Well, ways to reduce risk. Obviously, number one, become informed of the risks that are possible. Think critically about the risks, and also make careful choices. So the greatest health risks come from poverty, gender, and lifestyle choices. So poverty, by the greatest health risk by far. Malnutrition, increased infectious diseases, and unsafe drinking water. All right, we spoke about this a little bit in the first part of this unit. We've talked about how poverty is a big issue with a lot of things in environmental science, and when it comes with health risks, poverty number one. So obviously we want to reduce poverty around the world as much as possible, and that would reduce health risks to the human species. Gender, okay, being born male is actually a health risk, believe it or not, compared to being born a female. Lifestyle choices, examples, overeating and smoking, okay, or unsafe sex. All right, these are lifestyle choices that you choose, and of course, they have the greatest health risks. Okay, so again, poverty, gender, and lifestyle choices. This is a very interesting graph. So this is for the world. Okay. And what this is showing is the annual cause of death by these certain things. So you'll notice poverty, malnutrition, the disease cycle is the number one killer out there. You'll notice air pollution, number two, tobacco. All right, now, that's a personal choice, right? Smoking, that's a lifestyle choice, okay? But unfortunately, that's killing the third amount of people on the planet. All right, pneumonia and flu, we spoke about that. Okay, those are your infectious diseases, and et cetera down the line there. Okay, you'll notice the littler chart here. This is lack of access to adequate sanitation facility. 2.6 billion people don't have or have lack of access to adequate sanitation facilities. 36% of the world's population. Okay, enough fuel for heating and cooking. About 27% of the world's population has lack of access to this. Lack of access to electricity, 27%. So again, all these issues, okay, lead to that poverty and lead to that annual death rate up at 11 million. This number is very interesting. This number in red, okay, is the death. So basically, to put this in perspective, 151. So basically, the amount of death toll for the year, 11 million from poverty, malnutrition, and the disease cycle, is equivalent to 151 airline crashes each day. 200-person airline passenger crash each day where there are no survivors. Think about that. Think about it. We have an airline crash and it's wall-to-wall news coverage for 2 weeks, right? But yet, where's our news coverage from the amount of deaths from poverty and malnutrition when it's equivalent to 151 plane crashes per day for an entire year? Air pollution. The people who die yearly from air pollution is equal to 96 plane crashes per day for the entire year. Think about that. The number of people dying from tobacco, again, this is a personal choice of smoking, is equivalent to 82 airline crashes per day with no survivors for the entire year. Think what would happen if we had 82 airlines crash today. Think about the news coverage around the world that we would get for 82 airlines that crashed today with no survivors. How much coverage do we get about the people dying from tobacco use? All right, so again, this is an incredible number here, an incredible way to put these deaths in perspective and to understand why we need to change what we're doing. All right, this is the U.S. per year. All right, so that was the world. This was the U.S. Tobacco use here in the U.S., number one. And why? Because we don't have a lot of poverty here in the U.S., right? Okay, so poverty and malnutrition, not going to be the biggest one for us. All right, air pollution, not as huge for us because, believe it or not, our air isn't as bad as maybe in some underdeveloped countries, okay? So what do we come first? Tobacco use. Wow. And that's a personal choice, right? Then next comes your accidents, then your flu or pneumonia, then your diabetes, all right? Then down to alcohol, prescription drug, and illegal drug overdoses, all right? So again, just kind of understand, obviously you don't need to memorize these numbers, but I would understand that when it comes to around the world, poverty, malnutrition, number one cause of death, air pollution 2, tobacco use 3, definitely want to kind of put that into your memory. So going into that, a case study in the chapter talks about cigarettes and e-cigarettes. So cigarette smoking, the most preventable major cause of suffering and premature premature death among adults. Killed 100 million people during the 20th century smoking cigarettes. Study linked to increased dementia and Alzheimer's disease as well. Nicotine, a highly addictive drug. There have been studies that show nicotine is more highly addictive than cocaine. Okay, believe it or not. Yet nicotine, no problem. We'll sell cigarettes all over the place, right? Luckily, you got to be much older now than when I was your age. 18 was the age. Now it's 21. All right, but still, okay. Think about that. 100 million people killed during cigarette smoking last century, and that's a personal choice. That's a personal choice, okay? You don't have to do that. In addition, secondhand smoke poses a health hazard. That's not a personal choice, all right? Those folks who are experiencing inhaling secondhand smoke, it's obviously not their fault, and that's why, for instance, you can't go to a bar here in New York State and smoke cigarettes anymore. When I was your age, when I was in college, okay, over 21, of course, going to bars. I'd come out of the bar at 1 o'clock in the morning and I would reek of cigarette smoke. I didn't smoke, but I would reek. I would go home, my hair back to my dorm, the hair would smell, my clothes would stink of cigarette smoke. Okay, is that fair to me? I didn't smoke. All right, so obviously now you don't have to deal with that, especially here in New York State. So we've realized over the past 30, 40 years that not only was the smoker getting all these toxic chemicals, but the person next to the smoker was getting those secondhand smoke. So obviously we realized we had to do something with that. Smoking has declined in the U.S. from more than 50% of adults in 1950. Think about that. More than 50% of adults in the 1950s smoked cigarettes. Now we got about less than 18%. So the smoking has declined substantially here in the U.S., even overseas. I remember when I was younger and I traveled overseas to Italy and France, people were chain smoking. I remember I was 15 years old. Everyone had a cigarette in their mouth, everywhere. When I went back in 2009 with my wife, which is a while ago, but over 10 years ago now, Italy, no one smoked. It was incredible. It was incredible. So even in Europe, people have begun to realize this. All right, so e-cigarettes, obviously. A new thing now, substitute for tobacco cigarettes, but unfortunately the vapors do contain some toxic metals. E-cigarettes are used by more than 13% of high school students in 2014, and the European Union has banned the sales of e-cigarettes to minors, and I believe many states in the U.S. here have also banned the sale of e-cigarettes to minors as well. So how can we estimate risk from technology? So we spoke about infectious diseases, risks from that. We talked about risks from toxic chemicals. Now we're going to talk about risks from our technology. So how can we estimate that? Well, we can use something called reliability. The system reliability percent is equal to the technical reliability percent times the human reliability. What we're finding is the human reliability is much lower than the technological reliability, and obviously much harder to predict. Okay, so the human part of that formula, the reliability formula, much harder to predict than the technological part of that formula. Most people do a poor job of evaluating risks. Factors that cause misjudgment in risk: fear, okay, degree of control, like we want to have control, whether a risk is catastrophic or chronic, all right, optimism bias, obviously, and instant gratification are all ways that we as humans do a poor job of evaluating risk. So guidelines for evaluating and reducing risks as we go forward: we need to compare risks, okay? We need to determine how much of a risk you are willing to accept. You need to evaluate the actual risk involved, and you need to concentrate on evaluating and carefully making important lifestyle choices. So if we can follow these guidelines, okay, we have a better chance of reducing that risk, or at least understanding how to reduce that risk if we follow these important guidelines. All right, so that is the end to Chapter 16, Environmental Hazards and Human Health. I hope you enjoyed, and as always, thanks for listening.